Hi, my name's Mitch Golden. I am a PhD in theoretical physics who used to be a professor, and this is my presentation entitled Global Warming, the Persuasive Physics. So why was I motivated to write this talk? It's really aimed at two different kinds of people. The first are people who don't believe that human-caused global warming exists. My goal is to try to avoid preaching to the choir and to try and see if I can give to those people a scientific basis for the claims that one hears all the time about climate change. The second, of course, is for people who do believe that human-caused global warming exists, but who don't actually understand the science and who would like to learn. My point is really that there's a lot of stuff on the internet and elsewhere about global warming, but I personally have found it dissatisfying with respect to the physical explanations of global warming, and in fact it's the physical explanations that I find really persuasive. I think that one reason that the public discussion on global warming is really not very good is that there's just not enough physics in the public discussion. It allows people to make all kinds of crazy claims. That's really a shame because the physics of global warming is not at all hard to understand. And my hope in this presentation is to bring the science to the public in the way that the lay public can actually understand. So, why is there so much confusion about the subject of global warming? One of the sort of fundamental issues is that people think that the climate system is too big and complicated for us to make statements about. You'll hear people say things like, how can we say anything about the year 2100? After all, we can't even predict next week's weather. Well, that is true, but it's irrelevant. The goal of climate science is not to predict the weather 100 years from now. Here's a good example. Here are two pictures, and if I were to ask you which of these was created in December and which was created in May, you would have no difficulty telling me. Now, really the goal of climate science is to do nothing more than to explain why December tends to look like the picture on the left and May tends to look like the picture on the right, at least in the place where these pictures were painted. That is really a lot simpler than trying to understand why it might have been that on the day depicted on the right it was sunny and pleasant rather than cool and rainy. That's not on the agenda for climate science, so it's actually a lot easier than the goal of predicting the weather 100 years from now. So, if that's true, then we can begin to understand how science actually works in a sort of general way. We do actually understand very, very complicated systems. Many systems are at least as complicated or more as climate, and we have made great progress in understanding and using them. For example, I made a list of a few. How, without understanding something very, very complicated, could we build highways? To build a highway, you need to know all kinds of things about how cars work, how they perform when the pavement is wet or dry, how people's reaction times change day and night, etc., etc. And yet we build good highways, I should add, that are much better than the ones that were built, say, 70 years ago when they were first starting to do them. Or, how do we fly airplanes? Doing it for over 100 years, and aerodynamics is an extraordinarily complex subject and not at all possible to really make predictions of details, and yet we can nonetheless fly airplanes. Or even better, how do we practice medicine? Nothing's more complex than the human body, and doing medicine even depends on understanding how people think, not just the many thousands of chemical reactions involved in the human beings. So it would seem that we couldn't make any statements about medicine, and yet we live a lot longer thanks to a great deal of progress that's been made in medical science. So as it turns out, in science, there are really no systems that can be understood exactly. Everything in the world that's interesting is always fraught with too many complexities. So what we do instead is called building a model. We make approximations and simplifications, and we come up with a system that represents the one we want to understand, but is simple enough to actually analyze. That's called a model, and models are approximations. What that means is that you have to check that the model is capturing the behavior you want and that it will give you the answers to the questions you need. Sometimes we iterate. We make more and more complex models to get more and more detailed understanding of systems we want to analyze. So let me give you an example. Every day in the morning I take the bus, and the bus always seems to arrive late. And when it finally does arrive, it's immediately followed by another bus right behind it. So my question is, why does that happen? Now, to really understand that behavior, I would have to analyze everything about the bus, the traffic, the pedestrians, the lights. It would be an extraordinarily complicated problem, and I could never get my arms around it. But even in that chaos, there's a real way to simplify and answer the question.
So this is what I call the ABC model of buses, simplest possible model. Rule A, a bus moves through traffic at more or less a constant rate, except when it stops to pick up passengers. B, the more passengers there are waiting, the longer it has to stop. And C, the number of passengers at a given stop is larger the longer it has been since the last bus stopped at the stop. So what happens in this model? So situation one, we have the buses leaving the depot equally spaced and progressing through traffic, making their stops indicated by the little triangles under the road. Situation two is the middle bus of this group of three I'm showing here stops for a little bit longer. Somebody maybe argues with a driver or something, and it's now behind where it would have been. But from now on, as the middle bus travels, it is going to be encountering bus stops with extra people at it because of rule B. And so its progress through its route is now slower than it would have otherwise been. It will fall behind its scheduled arrival time. Meanwhile, because it's doing that, the third bus is going to encounter fewer and fewer people at its stops it's making, because the middle bus was there recently, and so it will now start to go faster than originally anticipated. So it will be catching up to the middle bus, and the middle bus will be slowing down, and so eventually, boom, the two of them come together. So what this model shows is that the system is subject to what's called a positive feedback. A positive feedback is a situation when a change that you make, a little external change like when the middle bus got held up, makes more of that same change. It amplifies itself within the system. So in this case, it was that the middle bus got behind schedule, causing more people to be at the stops, causing the bus to slow down, causing the bus to get further behind schedule. And in this system, the positive feedback affected both the second and the third buses, but in opposite ways. The third bus got faster, the second bus got slower, and they wound up together. That is indicative of a positive feedback, not meaning positive in the sense of, hey, this is a good thing, but just an amplifying feedback. There are systems with the opposite effect. That is, you push a little bit on the system, you make a change to it, and it behaves in the opposite way. It resists the change. Those are called negative feedbacks. Now, this model has limits. It doesn't fully describe the world of buses. Lots of things it didn't tell us. It didn't tell us why the bus slowed down, or things about the behavior of the people as they're waiting, like do they abandon waiting for the bus when it's late. It doesn't say at all, and probably the most important question here is what happens when the last bus catches up to the middle bus. We don't know, based on our ABC rules. And if we want to answer these questions, we need a more complex model that includes more of the physics, shall we say, of the bus system. And we may or may not be able to get everything right in terms of the behavior of the full bus system with respect to any of these questions. That does not mean that our model was wrong or useless, not at all. It explains what it's asked to explain for the right reasons. It gets the correct result regarding the buses coming together, and it explains that it has to do with the positive feedback.
So let's do the same kind of thing for climate that we just did for buses. So, what are the physical considerations we would need to put into any model of climate? Well, first, let's think we're modeling the climate of the Earth. What's the first thing about the Earth? Well, it's isolated. It sits in space. The Earth plus the atmosphere is surrounded by a vacuum, and it's at a temperature because it's getting energy in one way essentially only, which is from the sun by absorbing sunlight. There's no real other significant sources of energy. The other stars are too far away, etc. And it stays at a constant temperature because it releases energy back into space, actually, as we'll see, in infrared radiation back into space. And it has to be radiating, on average, the same amount of energy out that it absorbs from the sun, because if it were radiating on average more than it got from the sun, it would be losing energy and getting colder. If it's radiating less energy, then it would be accumulating energy and getting hotter. So there's a balance between radiation out and radiation in. So a little bit of a scientific, a technical aside here. How do bodies radiate? Well, this is something actually you're familiar with, even if you aren't directly aware of it from, say, high school physics or something. The bodies radiate when they get hot, and the way they radiate depends on how hot they are. So, for example, when you have a log in a fireplace, it glows a dull red. That's because of the temperature it is. And an incandescent light bulb is brighter and sort of not quite as red because it's hotter. And the sun is even bluer, and that is because it's hotter than an incandescent light. So here's a graph of what I just said. On the x-axis we have the wavelength of light, and it's measured in a unit called microns. And here's the strength of the radiation coming off of the body the hot body. And notice both of these are logarithmic axes. That is to say, each one of these numbers is the same unit in length is actually a factor of 10. So you can see here 3 different selected temperatures: 10,000 degrees Fahrenheit, which is pretty much the temperature of the sun; 5,000 degrees Fahrenheit, which might be comparable to a lighting fixture; and 80 degrees Fahrenheit, which is more or less sort of the temperature of the room you might be sitting in, maybe a little bit higher than that. So look at the different curves. Here you see the sun has the most radiation, a lot more radiation than this 80 degree line, and even more than the 5,000 degree line. And as you go down in temperature, you notice the peak of the radiation goes further out. And again, as I said, this is the wavelength. So longer wavelengths means redder light. So the sun is a rather blue source compared to the infrared, to the the lighting fixture, the incandescent lighting fixture this one might be. And in the 80-degree room, if there's no sunlight coming in, it's all in the infrared range and essentially nothing in the visible light, which is why you can't see anything. You'll also notice one quick point, that the visible light corresponds to the peak of the sun's radiation. That's actually very useful to us, that we have eyes that can see where the sun is, and of course it's exactly what you'd expect. If we had eyes that didn't see the light that's around, it wouldn't be very useful to us. So, from those physical considerations, we're going to make what I call Climate Model 0, the gray ball model. It's the simplest possible model of climate. So we're just going to say, strip out all of the complexity of the climate system and say the Earth has no atmosphere. It's a single gray ball, all at one temperature. Maybe it's metal or something, so that it stays all at one temperature, the whole thing. And what temperature does it come to? Well, that's an easy question that sometimes assigned a sophomore undergrad class. Sunlight is just the amount of sun that is going past the Earth at the Earth's orbit is measured in watts per square meter, and that's a number of 1366, which is the amount of energy the sun is radiating as measured from where the Earth is. Now the Earth reflects, the technical term is albedo, it reflects about 30% of the sunlight that hits it. So that that light just bounces off the Earth and doesn't do anything to warm it. And so the Earth actually absorbs about 950 watts per square meter. And then you ask yourself the simple question, what temperature does a body have to be to emit the amount of energy the Earth is absorbing? That is 950 watts per square meter. And that actually is something you derive from the curves that I showed you on the previous slide. And the answer is 0 degrees Fahrenheit. So what is that? Well, that's not a great answer. The actual average temperature is about 56 degrees Fahrenheit. But on the other hand, given that the only other two temperatures in the problem were 10,000 degrees Fahrenheit, which is the sun, and minus 455 degrees Fahrenheit for space, the fact that I got from this really, really simple, trivial model, that I got 0 as the temperature of the Earth, is actually not too terrible. But if I want to do better, which I do, I'm going to have to make a more complicated model. So let's try to do that. We'll make a more complicated model that we'll call Model 1, which is Earth with an atmosphere. And here's a picture of the atmosphere from space, a beautiful blue band surrounding the planet. So what are the relevant physical properties now of the atmosphere? Well, the first point is it's a gas. What does that mean? Well, it's not a solid, so it's held down by gravity, which is why it doesn't fly away, but it holds itself up not through some rigidity, but just through its internal pressure. The only thing that holds the air up is the pressure of the air, is what holds the air up. And the third point that's relevant is that the air moves around and it mixes itself vertically up and down through storms or flowing over mountains. The air is not a still body. It's not still. It goes, swirls around and mixes itself quickly due to winds up and down. So what does that tell us? Well, because of gravity and the observation too that the air is holding itself up, it's going to be the case that air is at lower pressure the higher the altitude is. And that's the point of that is, look, if I'm sitting here at sea level, where I more or less am, the air is more or less, if memory serves, at 15 pounds per square inch. That means each square inch is supporting a column of air that weighs 15 pounds. But if I go up 1,000 feet, well, that point of the atmosphere is supporting a column of air that's lighter than the one that includes the bottom 1,000 feet. So that point up 1,000 feet will actually be less pressure than down here. And we all know that. If you ever go to Denver, the air is thinner, the pressure is lower, so that actually matches onto your everyday understanding. And here's another one. This is based on the fact that the air is swirling around. As the air is going to swirl around, it's going to expand if it goes up, because it goes from a region of high pressure to a region of low pressure, so that if you imagine a balloon that is floating up into the atmosphere, if the balloon goes up, it's going to expand because the air around it is at lower pressure. Now, air has the property that as it expands, it cools. For those of you interested in such things, it's because it does work as it expands. It works on the other air surrounding it. And so it cools off as it goes up. And you can actually calculate that you would expect that air would cool off by 5.4 degrees Fahrenheit for each 1,000 feet that it moves up. And that property of cooling as it goes up is called the lapse rate. And we all know there's a lapse rate, even if we weren't consciously aware of it. This is one of the cool things about physics, is that it explains things that you don't even know you didn't know. So if I showed you a picture of this picture here on this slide, you might not have thought much about it. But here's a thing that's kind of a little bit maybe should give us pause. Look, we have a river at the bottom of the valley. So the bottom of the valley looks nice and warm and sunny, and yet there's snow on the top of the mountain right there. They're right next to each other, and so how is it that it's cold enough to have snow on the mountain and water in the valley? A nice warm day in the valley and a cold day at the top of the mountain. Well, that's the lapse rate right there. You see it in this picture. And now you know it's because air expands as it goes up from where it was in the valley to where it is at the top of the mountain, cools off, and now it's cold enough to freeze snow, for the snow to stay frozen. Now, a little refinement I'll bring up here just because it's going to play a minor role later on. The Earth's surface is 3/4 water. There's a lot of water around. And so the calculation that I just did to get 5.4 degrees per 1,000 feet isn't quite right, because what's going to happen is at some point water in the air is going to condense and form fog or clouds like you see in this picture. And when water condenses, it does the opposite thing from when it evaporates, which is it releases heat. So you get a different behavior that's called the moist adiabat. The lapse rate is not as big as it would be if the air were perfectly dry. The temperature goes down more slowly with height, and it goes down more slowly with height depending even on the surface temperature. So this moist adiabat effect is stronger when the surface is warm than when the surface is cold. And if you measure the lapse rate of the atmosphere, you find that it averages not 5.4, but closer to 3.5 per 1,000 feet. So that's interesting input to our model. Here's the only other part that's going to let us figure everything out. And that is that the air in the atmosphere is actually opaque to infrared frequencies, but not to visible light particularly. So here, this is a graph from a NASA website that shows the transparency of the atmosphere as a function of the wavelength. And I've lined it up more or less with the graph that I showed you previously on how bodies radiate at the different temperatures. Here's visible light, and you can see, not too surprisingly, that the atmosphere is, especially in the yellows and red and more or less most of the blue, it's pretty transparent to visible light. Not completely transparent, but mostly. And that's good because that means that the light can get in and we can see the sun and so on. But in the infrared, you can see there are a lot of places where the atmosphere is actually fairly opaque, especially down here at the far infrared here. And mostly it's caused by absorption from different chemicals. Down here it's water, H2O. Here at the more or less the peak of this 80-degree thing, you see here's CO2. Then there's more. There's O3, which is ozone. H2O is also here, and CO2 is here again. So in these regions, you see that the atmosphere is actually getting to be kind of opaque to infrared. Now, here's another way of saying that. If we were up in far above the Earth, and I have a camera and I take a picture of the Earth from space, here is what it is if I have a regular camera. But if I take it with an infrared camera, then I can't see the surface. So this is 20 microns. I picked that as infrared. We saw it. It's opaque. So you can't see the surface. It's like trying to see the bottom of the ocean through the ocean. It's just not transparent enough for you to see all the way down. And what you're seeing is some point in the middle of the murk of the atmosphere. Just like when you look into the ocean, you see some point a few feet down. You can't see the surface. All right. So what does that all say? Well, here's the argument, and this will take us through. The atmosphere is transparent to the sun's rays, so when we put the atmosphere there, we didn't change the amount of radiation that was absorbed, and so we didn't change the amount of radiation that has to be radiated to keep the Earth in balance with the sun. But looking down from space, we're not seeing the surface, we're seeing some point above the surface. So what we're seeing radiate isn't the surface, it's a point above the surface, which is to say, before when we were doing our calculations, it was the surface temperature down here that we were calculating, because that's what's radiating. But now, what we're calculating when we calculate that outbound radiation is the temperature of some point up in the atmosphere, because that's actually what's doing the radiating for the Earth, not the surface. So to be in balance, the place that's radiating is going to still be 0 degrees on average, but because of the lapse rate, it's that point isn't the surface, so that point's up in the atmosphere, and we already agreed that point is going to be cooler than the surface. So the surface is actually warmer than the 0 degrees. And I'm not going to go through any calculation because it would sort of be bogus anyway. But you can see that means unavoidably that the surface is going to be warmer than 0 degrees. It's going to be warmer than it would have been if there had been no atmosphere. And that's because of this opacity to infrared that keeps the surface from being the thing that cools off, but rather this higher point in the atmosphere. Now, what would happen what is the role of CO2? What happens if we add CO2 to the atmosphere? Well, you see, these points are where the Earth is radiating, where those two arrows are. So if we add more CO2, we're going to make the atmosphere more opaque to infrared. And that means that the place that's radiating is going to be higher and higher and higher and higher in the atmosphere. That's what you see as you look down from space with my infrared camera. So you will warm the surface because that lapse rate keeps going, you're going higher and higher, and that lapse rate means that the difference between what's radiating and the surface gets bigger and bigger. Now, sometimes you'll hear people say, how can it be? CO2 is such a small part of the atmosphere. It's true. It's a tiny part of the atmosphere. It's only 0.039% of the atmosphere, which is the same as saying it's 5 3/4 inches as a fraction of the height of the Empire State Building. So pretty insignificant number. But that's actually sort of explains why humanity can do anything about it. Because CO2 is an insignificant part of the atmosphere, but and if we were trying to change the amount of nitrogen or oxygen or argon in the atmosphere, which is the vast majority of what the atmosphere is made of, we could never do it. But on the other hand, those chemicals don't have any effect on the infrared. They're not the things that are opaque. So it just doesn't matter. What's relevant isn't the fraction of the total atmosphere. It's what's relevant is the fraction of the opacity in the infrared. And so it's actually kind of working against us that there was so little carbon dioxide there to start with. That actually is what gives humanity the ability to make a change. So that's it. It's pretty simple stuff. You know all the concepts that came in. You basically understand that the lapse rate is a physical thing we all know. Radiation of warm bodies you see in a fireplace. It's all very simple concepts, very familiar stuff. And really, this is the argument that I just gave is something that is not doesn't really use any physics beyond something an undergraduate would get.
So the question we have now is whether this is big or small, is it significant or not. In order to do that, we have to attach some numbers to it. The way climate scientists usually talk about it is as follows. We know that the original atmosphere, say 300 years ago, before we started digging up coal and oil in significant quantities, was about 0.0275% CO2. The figure of merit that climate scientists will talk about is what happens if you were to double CO2 to twice the pre-industrial value, meaning 0.055% CO2. What would the Earth do if you doubled CO2 like that? And if you do the simplest computation, you would expect the temperature of the surface to rise about 2 degrees Fahrenheit, which is also known as 1.2 degrees Celsius. And knowing what we do about weather and ecology, 2 degrees Fahrenheit, 1.2 degrees Celsius is probably not too big a problem. It would have some serious effects, but we could probably live with them. The problem is that that's not the end of the story. And the complexity is that the Earth and the atmosphere are going to change as the planet warms up. And what we're going to find is that there are positive feedbacks of the kind that we saw in the bus system.
So what are those feedbacks? Well, what changes if the Earth warms? What would you expect to change? Let's think. We can probably think of some very simple stuff. Well, first of all, if the atmosphere is warmer, because warm air holds more moisture, that's something we're all pretty familiar with, we could expect the atmosphere to hold more moisture. Now, I say ouch. Well, ouch means uh-oh, positive feedback. We've seen water vapor was one of those things that's opaque in the infrared. And so if we expect more water vapor in the atmosphere as well as more carbon dioxide, well, then we expect even more than just the 2 degrees Fahrenheit. We would expect a positive feedback from the water vapor going in. And in fact, that's a pretty strong one. But what else? That's just one thing. Well, more water vapor and higher temperature mean a smaller lapse rate because of the moist adiabat. The moist adiabat means that the temperature gap between it as a high point and a low point is less a bit because of the effect of the water. So I say, whew, this will lower the difference in temperature between the surface and the upper atmosphere, so that cools the surface a bit. It's a negative feedback, and that will dampen the effect of the CO2. What else? We can keep going. Well, what happens? Well, ice tends to melt, of course, as you warm it. Ice is reflective, but what tends to be under ice tends not to be as reflective as ice. Ice is white. What's under a lot of the ice in the world is the Arctic Ocean. If you melt it, you can see right here what you're going to see underneath is ocean, which is quite dark. So you're going to increase the absorption of sunlight from the darkness of the ocean, that's going to be a positive feedback. And we can go on and on. In fact, that's what climate science does. It goes on and on. It tries to list all of the feedbacks involved in the climate. And if you're so interested, you can read. There's a pretty nice Wikipedia page on the subject. Of course, there are a lot of other places you can read about it. The goal of climate science is to figure out all of them and to see how big they are and how fast they're going to operate. And in the end, the term climate sensitivity refers to what you get when you add them all up. And so how warm does the Earth actually get when you double the CO2 to 0.055%? Some feedbacks are pretty well understood, some are not. But so there's obviously a lot of learning still to do about the Earth. But that being said, the water vapor and lapse rate feedbacks are very big and very fast acting, and they're pretty well understood. So now you have to ask yourself, okay, well, we can make this list, but even if I don't understand them terribly well, do they really look big enough to wipe out as a negative feedback the effect of the lapse rate and water vapor? And that's kind of limits you. You can't just have some little tiny feedback that you don't understand. You need a big one. What are possible big ones that you could think about? Well, clouds is something that climate science spends a lot of time thinking about because they have a very large effect on climate. If there are no clouds, the Earth would be darker, as is obvious from this picture. There's a lot of white in it from all the clouds. And if there were no clouds, the Earth would be darker and therefore hotter. And then you might say, all right, cool, more humidity, we already said, so more clouds. More clouds means negative feedback, right? Well, unfortunately, no, it's not that simple. Clouds are really complicated. They depend on all kinds of things, all the way from amount of dust in the air, the amount, maybe cosmic rays, moisture, of course. And then to top it off, there are all kinds of different kinds of clouds. This puffy white ones called cumulus clouds, or the thin, scraggly ones called cirrus clouds. And they have different effects. The puffy white ones are the ones you saw in that picture, and they reflect sunlight. So during the day, they're going to lower the temperature. But all clouds, since they're made of water vapor, are going to reflect infrared down to the surface, so they actually have the effect of raising the temperature of the surface at night. And the the cirrus clouds, since they don't really block the sun, but they do block the infrared, they raise temperature day and night. So you need to figure out what all that complicated stuff is. And you basically have to ask yourself, well, what happens to the clouds when if the Earth's warm? Where are they going to form? What kinds are they? What do they do to the water vapor? Do they function overall as a positive or negative feedback when you warm climate? Which is a different question than what happens if there were no clouds. It's a question of how do clouds change? And in fact, this was probably the single, I think, it was the single biggest uncertainty preventing a real solid scientific consensus until, through the 1980s. There was 1990 or so that you pretty much found that by that point, the direct measurements of clouds with satellites and so on, that while it's not completely clear, the understanding of all of the details of cloud formations, what we see in the direct measurements is that the simple models that the scientists have had for a long time actually describe clouds, as far as this goes, pretty well. They as far as their role as a climate feedback, there's a lot to still learn, but the climate feedback seems to be pretty well modeled. And what you find is that clouds are either a small positive or a small negative feedback. They don't act as a gigantic negative feedback, wiping out the full effect of the water vapor feedback that we know is a positive feedback. Now, when I say it's a consensus, that doesn't mean that you can't find somebody who has credentials to disagree. The old joke about two economists with three opinions applies. But in fact, among climate scientists and the scientific community in general, there really are a very small number of scientists who disagree with this. Generally, the disagreements are about clouds, in fact. These four gentlemen are Richard Lindzen, John Christie, Roy Spencer, and Patrick Michaels. You hear an awful lot from them, largely because the press tends to always want to find somebody to give the other side of every story, even if the other side is a distinctly minority view. And so you tend to find the same guys giving the minority view over and over again. And these guys are, I term them the most famous men in climate science because they keep getting quoted, even though they don't tend to be quoted in scientific literature. As an example of that, I would say if the press covered medicine the same way they cover climate science, this fellow would be the most famous man in medicine. His name is Peter Duesberg, and he is a rather distinguished individual. He's a member of the National Academy of Sciences, which is a rather high honor. He's a professor at UC Berkeley, and he does not believe that AIDS is caused by a virus. He believes that it is caused by recreational drugs. And you can take a look at his website, and you'll find that he feels that he's being persecuted and that there's groupthink, and that the only reason that his theories aren't taken seriously is that they're being discriminated against, and so on. You can come to your own conclusion about that sort of argument, but I sure would agree that he probably shouldn't be mentioned in every single article about AIDS. So I told you at the beginning that when you come up with models, you always have to check, because they are approximations. You're leaving a lot of stuff out, and you want to understand that you haven't broken the physical system you're trying to understand. So here's how do we know that we know what we're talking about? You need to check. Well, here's James Hansen, a rather well-known climate scientist from NASA, says in decreasing order of persuasiveness, how do we know what we're talking about? Well, the first is the paleoclimate. We know that, for example, there have been ice ages, and they know more or less when they were. And based on that, we actually have nowadays a pretty good understanding of what causes climate ice ages, and they're caused by something cycles in the Earth's orbit around the sun. Sometimes the Earth's orbit is more like a circle, sometimes more like an ellipse. Sometimes the Earth's axis points close, more obliquely, and sometimes less. And it precesses around, so it points in different points relative to the sun. So those things cause ice ages. And if you ask, how can they cause ice ages? Well, you only can understand how they would cause ice ages because these effects are not themselves big enough in terms of the amount of sunlight the Earth absorbs. They're not themselves big enough to cause the shifts in climate that ice ages represent. But if we know that there are positive feedbacks, and the positive feedbacks appear to be roughly the right sizes calculated by the kinds of models I just described, if we do that, then we can understand ice ages. And if we don't put in positive feedbacks, we can't understand ice ages. An aside is that the fact that the climate changes is sometimes used as an argument that because the climate changed in the past that we don't understand how humans could cause climate changes. And here's a quote from relatively recently from Rick Perry. Yes, our climate's changed. They've been changing ever since the Earth was formed. That's true, but it's backwards. The fact that the climate does change is proof that the climate is the sort of system that has positive feedbacks. If it had negative feedbacks, then it would not be easy to change the Earth's climate. It would be a very stable system that all these little tiny orbital changes would not be able to make ice ages out of. So the past changes are not magic. They actually are understood by science, and that science validates the understanding of climate. Now, how else do we know? Well, the climate is directly measured. We measure all kinds of stuff, not just including the overall surface temperature, but the lapse rate, the amount of clouds, and where they are, and how warm the ocean is, and when the ice caps are doing. All that stuff fits together and confirms our understanding that the Earth behaves in the way that we would expect it to if we put carbon dioxide in the atmosphere. The third point is that the computer calculations of climate models actually agree in detail with very specific observations. That we can't do experiments on the climate. We can't tweak the climate ourselves and say, well, how does it change? But the Earth occasionally does tweaks for us that we can actually use. And the most famous one of recent note is that in 1991, Mount Pinatubo erupted and put a tremendous amount of dust up in the atmosphere. And the effect of that dust is to make the atmosphere a little bit opaque to visible light, and thereby cool the surface of the Earth. And if you calculate and measure how much, we measured how much dust went up and how opaque it made the atmosphere, and we measured how much the temperature of the Earth declined, which it did the year after Mount Pinatubo erupted. And the only way you can understand the amount that the temperature declined is if you have the right level of climate sensitivity, the right amount of climate feedback. And it also agrees with qualitatively with the calculation both from the models, from the measurements, and from the paleoclimate. And just quickly, of course, there are other confirmations that we have that show us that this is happening. We see something that we have cooling of the stratosphere. The very upper atmosphere is cooling off, and that's actually something one predicts in the global warming through greenhouse gases model. We see more warming at the poles in the tropics. That's called polar amplification. This chart shows you how much warmer the decade of the 2000s was relative to the 1950 to 1980, and you can see that the reds are all up at the northern latitudes. We see more nighttime warming than daytime warming, all of which are things if you think about it and press on this model more than I'm going to do in this presentation, they're all things you would expect, and they're all things that have been observed. And frankly, they're all also things that you would not expect. They're the opposite of what you would see if the warming were caused by the sun, as sometimes is suggested. Because, for example, if the sun were warming up and getting hotter, well, that would make the tropics, which gets a lot of sun, warm, but not the poles, because they don't get a lot of sun. What's the consensus value of climate sensitivity? This I'm showing here the detailed statement from the Intergovernmental Panel on Climate Change, a UN body that summarizes the literature, and the answer pretty much is that the science best guess value is that it's 5.4 degrees. If you go from the pre-industrial value of 2.8%, 0.028% CO2 to 0.055% CO2, we expect the planet to warm by 5.4 degrees Fahrenheit. And this prediction has moved around a little bit, but more or less it's actually been fairly robust. The science has been getting better and better, and it hasn't moved this needle very much. It's basically unchanged as a prediction since 1979. All right, so why do you care? Well, here's a statement I sometimes hear. Yeah, I hate winter. Why do I care if the Earth warms by 3 degrees Celsius? And the answer is because the secondary effects of climate change are much worse than the temperature rise itself. We've heard the litany, lots of effects that are not fun. Melting ice on Greenland and Antarctica will raise the sea level, inundating coastal regions such as the beautiful tropic isle depicted on the right. There's also ocean acidification, which will play havoc with ocean life and species extinction and tropical diseases moving, all that stuff. But I am going to stay focused on physics because I'm a physicist and I want to show you the persuasive physics. The most important change, I think, is actually easy to understand from physics. If the atmosphere is warmer, we already said this, water will evaporate faster. Therefore, if it's not raining, it's drying out faster than it would have. So unless there's more rain in any given location than there was before, if that location has gotten warmer, it will be drier. So there'll be longer, more intense droughts. The picture is a picture of the Midwest during the Dust Bowl when there was a long and intense drought. 2, there'll be more water in the atmosphere. So there'll be more precipitation. But not necessarily where it used to be, I should point out. There's no reason to assume that the precipitation stays where it is. That's a hard thing to get exactly right, but there's no reason we shouldn't expect that water will be where we want it. But here's the other point, that storms will actually become more intense. We should expect storms to become more intense. And here's a picture of a rather intense rainstorm rather than a nice gentle one. Why would water in the atmosphere be dangerous? And I like this because this goes back to like that picture of the mountain and the valley. It's something you weren't thinking about, but suddenly if you think about it, like whole things in the world understand. It's a really deep point, which is that mechanical equivalent of heat is a big, big number. What's the mechanical equivalent of heat mean? It's imagine you want to take energy and you're either going to use it to warm something or you're going to use it to make motion. Well, you can make a lot of motion with the amount of energy it takes to make a small amount of warming. So the energy unit we use in this country to measure energy is called the British Thermal Unit, or BTU, and it's defined as the amount of energy it takes to raise the temperature of a pound of water, which is about a pint, 1 degree Fahrenheit. Well, that amount of energy would make a car go 3 miles per hour. So take that cup of water, raise it that's a pint there. That pint, raise it 1 degree Fahrenheit. That car, my first car, a 1984 Ford Escort, would go 3 miles an hour. I said this is really deep, and like I said, there's lots of stuff that you can mean, but one of the things you can understand is it explains why the brakes of your car don't melt, because you are going really fast, and it's a really heavy thing. It's a car. It weighs over a ton, and the brake is this little kind of pretty small piece of metal around the 4 wheels, and you can stop the car, and it warms the brakes up some, but it doesn't melt them or anything. A mechanical equivalent of heat is even more extreme if we're thinking about how much energy it takes to evaporate water. It takes a lot of energy. If I wanted to evaporate, just leave that cup standing in a room. Don't boil it. Just leave it standing in a room. How much energy has to enter that cup to evaporate all of the water out of the cup? And the answer is the same as it would take to get that car going nearly 100 miles an hour. So you can make a lot of motion for the same energy as it takes to make not much temperature. So more water vapor, more evaporated water, means that there's a lot of extra energy in the atmosphere. And I'm not going to go into the physics of storms, but you can understand there's a strong plausibility argument just from the energy consideration that based on the fact that there's more energy around, that you would expect the storms to get stronger and to be more intense. And I can add, because this comes up all the time, there'll be more blizzards too. More deluges will mean more blizzards, because as long as it's wherever you are still cold enough to go below freezing, at least sometimes, then when it's below freezing, if you get a storm, it's going to be a snowstorm, and if it's going to be an intense or more intense snowstorm, it's going to be a blizzard. The bad news is that there's about 4% already, 4% more water vapor in the atmosphere than there was 30 years ago. And as for the future, here's a quote from a pretty well-known climate scientist at the National Center for Atmospheric Research, Kevin Trenberth, who says, "And so when you start talking about 3, 4, 5 degrees Celsius of temperature rise, which is what we are talking about, then you're talking about 20% increases in the water vapor in the atmosphere. The intervals between storms will be longer, but then when you do have the storms, they're apt to be a doozy. So you can really get deluges, and there are times when you have longer dry spells in between, so there's risk of drought if you happen to miss these storms. But then when you do get hit by them, suddenly you've got a deluge." And I will tell you, even physicists know enough about agriculture to tell you that droughts followed by deluges is not good for farming. So that's a pretty serious concern about our ability to do agriculture as the climate changes. So now I just wanted to conclude the presentation with a sort of guide to who to believe when you hear stuff about climate. And I can add myself in this. Who should you believe? There are a lot of shrill voices out there, a lot of them get covered in the press, and it's hard to tell who you should be paying attention to. Who is the most reliable, and who do you want to trust? Not the politicians. It's not their job. They may believe what they're saying, they may not believe what they're saying. Doesn't matter. Their job is different. They're, at best, trying to repeat something they heard from someone else. Not the editorials. Editorial writers are also not scientifically qualified, and they will be able to find people to tell them what they want to hear. And in any case, you don't need the filters. There are better places. Who should you get it from? Not even the individual scientists, because like I said, unless you know the scientific literature, you don't know which scientists to listen to. But there are lots and lots of scientific organizations consisting of many, many hundreds of thousands of members, and they are the ones you should be listening to. And I have here a list, it's from Wikipedia, of all of the scientific organizations that have issued statements supporting the consensus view about human-caused climate change being caused by emission of carbon dioxide and other gases. And it is a gigantic list. And you can see that national academies of sciences of all these different countries, including the U.S., I highlighted that in red, all these climate change has been validated by all the physical societies, the chemical societies. The American Geophysical Union is the relevant body in which the climate scientists would be members, and so on. And there are no actual scientific organizations that are making currently any statements in opposition to the scientific consensus as demonstrated here. Now, why should you listen to the scientific organizations as your guide? And it's not because they're filled with smart eminences. I show this picture of, I'm a physicist. This is probably, in my view, the most eminent collection of physicists and possibly the smartest group of people ever to appear in a single photograph. You may not know all of them, but just to name a couple. That fellow is Albert Einstein, that's Marie Curie, and they were busy discussing quantum mechanics and the foundations of 20th century physics when this picture was taken in 1927. But even as people as smart as this can be wrong about science, and in fact Einstein was wrong about a lot of stuff he believed. So it's not because they're so smart, it's actually because the scientific organizations are slow-moving and conservative in the real sense of that word. They don't make sense, they have processes, and they don't make statements that can't be supported by what's in the published literature, what's been carefully refereed and gone through a process of validation through a building of consensus. That's why you should believe them and not one particular scientist or an editorial writer. So my real conclusion is, you've heard the talk. Now, when you hear somebody saying something about global warming is a hoax, or that he doesn't believe global warming, your response, polite response to him, her, should be this. I understand what you're saying. Let's not talk about all the politics and theater about stolen email or fraudulent data, all that stuff. Here's the simple physics. The simple physics that have been laid out in this presentation. The opacity of CO2 to infrared rays and the fact that the atmosphere is colder higher up gives us the physics we need to understand why we expect the temperature to increase as CO2 increases. So if you want to persuade me that there is no such thing and that the climate won't change, please tell me what you think is the strong negative feedback that's going to cancel out the simple, well-understood positive feedback caused by water vapor. Please tell me, in the presence of that feedback, why we've had ice ages. How is it that the climate has been variable in the past? And I would say the most important question for you to ask is, if somebody is saying that climate change is a hoax, please ask that person to tell you why it is that none of the scientific organizations of all around the world have been persuaded by the scientific arguments being made that there's some way that climate change can't happen. I hope you've enjoyed my presentation. I hope you learned something from it, and I welcome comments and constructive criticism. Thanks.